Okay, we want to approximate the area under the curve over the given interval using 4 left endpoint rectangles. Use the provided graph to sketch the curve and the rectangles. So we start off by graphing this equation. You can use your calculator to help if you need to, but we're going to start at 3 and go down 1, right 2, doing the best we can. The more points you make, the less likely you'll have to come back and add more points. Oops. Later. And then draw your line. My line's probably going to look pretty bad because I'm drawing this on an iPad. There we go. Okay, we want to go from -4 to 4. So here's -4, here's 4, drawing left endpoint rectangles. And so that means each rectangle is going to be 2 wide. We're going to draw up on the left side until we touch our graph and then come over. Now that we've got our rectangles drawn, we want to figure out what the area of these rectangles are. Since they're all 2 wide, we can just multiply by 2 at the end and times by their lengths. And so for their lengths, we look at the top of our rectangles. So like we look at this point up here, which is 7. And then the next one, that's not a 7, that's a 5. And then the next one, which is 4. And then 3. And then 2. We've got 4 rectangles, so we've got 4 things to add together, and then we're going to multiply by 2 and get our answer, which is 28. The last one we might not have needed to graph, but this one, like we might not have needed the calculator to graph it, but on this one we're probably going to want to, and if we do, we just look at the table of values and graph our points. The vertex, which is the bottom of our graph, is at 1, 1/2, around there. And then on either side, at 0 and 2, it goes up to 1. And then we go up to 2.5. And then 5. And then 8.5. And we don't actually have to go all the way up with that on both sides, but if you look at your interval between -3 and 1, like we definitely need to go up on the left side. And so if I draw this hopefully kind of nicely, something like this. Now this time we're supposed to do 4 right endpoint rectangles, and so the easiest way to do it is to start from your right side. Now since there's 4 and we've got 4 spaces, each will be only 1 wide, and so my first rectangle, I drew it down too far, but like my first rectangle only goes up to 1/2. My second one should only go up to 1, and then it should go up to 2.5, and then it should go up to 5. And so they're right rectangles because they're going up on the right side and touching our graph. These are all 1 wide. We started with 1/2, 1, 2.5, and 5. If I add those together and times by 1, I get 9. This time we're doing midpoint rectangles, and we just start off by graphing. This time our vertex is at 0, 12. And then it goes down to 11 on either side, then 8, and then 3. Our rectangles are supposed to be between -1 and 3. So here's -1, here is 3. So we've got 4 spaces, which means they're each 1 wide. Now, here's what's tricky about midpoint, is that we're not going up on the left or the right, we're actually trying to go up in the middle. And so it doesn't matter which side you start off from. Like, I want to go up at -0.5 and figure out where the top of my graph is, where it touches my graph if I'm at negative 0.5. And unfortunately, if it's a parabola and our rectangles are only one wide, we probably are going to have to look this up on our calculator to see what the value is at 0.5 for negative 0.5 and positive 0.5. We're probably going to have to look it up. And from there, we might be able to guess what the other two are, but it's actually safer to just keep looking them up. So if I follow at 1.5 up, it looks like it happens at about almost 10, but not quite. Somewhere in this box is where that one ends up. And then the next one is almost 6, but not quite. So your rectangles don't have to be perfect there, as long as you're willing to look up what these are. At negative 0.5, so if you have an y equals, and you go to your graph, and you press trace, it will let you type in values. So if you type in negative 0.5, it will tell you that that's 11.75. If you type in positive 0.5, it will tell you that that's 11.75. If you type in 1.5 for the next one, that's 9.75. And then the last one is 5.75. But you're not going to be able to get those decimals if you don't know that, hey, I'm looking for what's in the middle of these rectangles, so I'm going to have to plug in a number that's in the middle, which is a 0.5 of some sort. If I add these all together, I get 39. Evaluate each indefinite integral. So we're going to start off with a little power rule. It's indefinite because it doesn't have numbers, which means at the end of this we'll have to put a plus c. On number 4, we're going to add 1 to our power and get 4, and then divide by that 4. So that's going to be 12x to the 4th divided by 4. Now that's going to simplify in the next step. On negative 10x to the 1st, we do negative 10x squared divided by 2. Then whenever we come to just a number, that has to have an x with it. Anytime you just have a number in an integral, you put an x with it. And so it's because it's like there's an x to the 0, and so when you add 1 to 0, you get 1, and then you divide by 1, and it's still the same thing. So we should end up with 3x to the 4th minus 5x squared minus 2x plus c for our answer. On 5, this looks tricky, but if you can remember that, like, this 7 over 2 thing that's happening is like 7 halves x. And so what we need to do is add 1 to our power. So to add 1 to 5 halves, I need a common denominator. So I'm going to add 2 over 2, and I get 7 halves. So that's my new exponent. And then I'm going to divide by 7 halves. Well, 7 halves divided by 7 halves is just going to cancel out. Then I do this again. I'm going to put 16 over 5 and then figure out my new exponent. To add 1 to 3/5, I need to add 5 over 5 and get 8/5. So I divide by 8/5. Those don't cancel out completely, but the 5s will cancel, and we'll do 16 divided by 8 and end up with a 2. So this one, they both canceled. So we have x to the 7 halves. This one, 16 over 8 becomes 2, x to the 8/5. And then finally, I have 9 halves. I'm going to add 2 over 2 to 1/2 and get 3 halves. Divide by the 3 halves. So the 2's cancel. And we get 9 divided by 3, which is 3. So this is plus 3x to the 3 halves plus c. Number 6 is another power rule. Even though it's negative exponents, we can still add 1 to them. And so if I add 1 to negative 2, I get negative 1, and then I divide by negative 1. It's really important that you divide not just by the 1, but by the negative, because we have to divide by what our exponent becomes. On this next one, we've got negative 8. When I add a power, it'll be negative 4. And then we're going to divide by negative 4. So this first one, that gives us 3x to the negative 1. These two negatives will cancel each other out and give us plus 2x to the negative 4th. That's one way of writing our answer. The other is to say, well, I don't want negative exponents, so I'm going to move these back well, not back. I'm going to move these down to the bottom and make them be 3 over x plus 2 over x to the 4th plus c. So those are both acceptable answers. The second one is technically a better answer because it doesn't have negative exponents. Number 7, if you try to power rule this because you're like, oh, I'm just going to bring this up to the top because that's a really cool thing we can do. If you try to power rule this, when you add 1, you get 0, which isn't the worst thing in the world. But then when you divide by 0, that's not allowed. So this is not a power rule, which means we have to come up with something else. So when just an x to the first power is on bottom, this turns into the natural log of what's on bottom. And so the negative and the 4 in front and on top need to go in front and on top of our answer. So this is negative 4 ln x plus c, or another way to write it would be to have absolute values around the x. If you forget the absolute value bars there, that's okay with me. Just keep that in mind. Number 8, the integral of e to the x is e to the x, because e to the x is awesome like that. So what's in front stays in front. Negative 4 e to the x plus c is our answer. Whenever it's a number other than e, what we have to do is put a 1 over the natural log of what our number is in front. Now, the negative here is not really like there's a difference between us having negative 5 to the x and us having negative 5 to the x. And the problem is that a lot of times we forget that, or maybe we just don't realize that that's a difference. If I have negative 5 without the parentheses and I raise it to the x power, I do 5 to the power and then I automatically make it negative in front. But if negative 5 was in parentheses, I'd take that negative and have the power affect it as well. All that is to say is that since they wrote it this way, my negative from in front of the 5 to the x is going to be in front, and only 5 is part of my actual, is the a part of our formula. There's a formula for this that says the integral of a to the x dx equals 1 over ln a to the x plus c. So if I follow that formula, I'm just trying to point out that a is just 5. That negative goes completely in front, just like if there had been a 2 in front, like if this had said 2 times 5 to the x. Well, the 2 is extra and goes in front. So this is our answer right here. Trig function. So we have to figure out how to go backwards. We knew what the derivatives of each trig function were. Now we're given the answer and we're trying to work backwards. So what goes with secant x tangent x is secant x plus c. On 11, it's not quite that simple because we don't know right off the bat what the integral of this is. So before we actually figure out what it is, we have to use some trig identities. And so we're going to split this up into negative 2 times cosine x over sine x. But if I just have cosine x over sine x and I don't put this squared, that means that I still have another sine x on bottom. So I'm just separating basically what this is into 2 different fractions, because if I know my identities, cosine over sine is cotangent, 1 over sine is cosecant, and this has an integral. The integral of cotangent x cosecant x is negative cosecant x, and since this has a negative 2 in front, that's going to make it positive 2 cosecant x plus c. 12 is another one we have to use an identity for. So if you use an identity to bring this up to the top and say that this is really negative sine x, because sine and cosecant are reciprocals of each other, you haven't done any calculus yet. That's trig. So now that we are done with our trig, we can do our calculus and say, what's the integral of negative sine x? And our answer would be cosine x plus c. 13. Now this looks super complicated. There's a formula that goes with this, and so this one matches inverse secant, and it actually matches it perfectly because this is u squared minus 1, like all of this is. On top would be u prime, since u is just x, u prime is 1, and so this already matches what we want, so this is inverse secant of x plus c. On 14 and 15, it's a little trickier. We have to think about what we know from our formulas. Like 14 is the formula for inverse tangent, and so that formula for inverse tangent has the integral of u prime over 1 plus u squared du equals inverse tangent of u plus c. So we have to know how to use this formula, and so what matters is that I want a 1 here and it's not, it's a 16, so the first thing we do is we take out that 16. That gives us 1 over 16 times 1 plus x squared over 16. And what that does is it gives us 1 plus u squared on the bottom right here. And so since that's supposed to be 1 plus u squared, this has to be u squared. U squared equals x squared over 16, which means u, which we'll need whenever we fill in our formula, is x over 4. The other thing we need to know for our formula is u prime. The derivative of x over 4 is 1 over 4. So here's what needs to happen. When I look at what I have in my problem, I have a 1 on top and I'm supposed to have u prime on top. U prime is 1/4, so let's multiply the top by 1/4. And that means I also have to multiply the bottom by 1/4. So now what we have is a 1/4 on top. 16 times 1/4 can cancel and give me 4. And then inside my parentheses is still 1 plus x squared over 16. So I have u prime on top, I have 1 plus u squared on bottom. All of that ends up turning into inverse tangent of u, which is x over 4. But I have something left over here on bottom. This 4 is extra on bottom, and I put that in front of inverse tangent as 1/4. If it was an extra 4 on top, that would be a regular 4, but an extra 4 on the bottom of a fraction is really like a 1/4. And then I put plus c, and that's my answer. Number 15 works pretty similarly. This formula is for inverse sine, and it has u prime over the square root of 1 minus u squared. And so what we want to do is get a 1 right here where this 4 is. So it works really similarly that there's a number that's not 1 that we want to make 1 on each of these problems. So I'm going to take that 4 out, and I'm taking it out underneath my square root, at least initially. I can move it out here in a second, but that gives me the square root of 4 times 1 minus x squared over 4. So now I know what u squared is. U squared is x squared over 4. And so u would be x over 2. U prime would be 1/2. So we can do a couple of things now. One thing we can do is that 4 inside of our square root really doesn't need to be inside. So let's move it out and say, well, the square root of 4 is 2. So this is 1 over 2 square roots of 1 minus x squared over 4. And then let's go back and say, all right, what do I have left for my formula? I need u prime on top, so I need to times the top by 1/2, which means I times the bottom by 1/2. Well, 2 times 1/2 is going to cancel out. So on top I have u prime, which is 1/2. On bottom I have square root of 1 minus u squared. All that's left is a 1 on top and a 1 on bottom, so basically all I have is 1 inverse sine, or just inverse sine, of, I didn't like the way I wrote that, inverse sine of u, which is x over 2. Now let's do some definite integrals. So definite integrals, we don't end up putting plus c because they have numbers for us to plug in and we end up with a number answer. So we start off the same way, taking the integral and using things like the power rule or changing to natural log or things like that. So on 16 and 17, these are power rules. So you add a power and then divide. So when I add a power to 2, I get 3, and then I divide by 3. Then this is negative 4x squared over 2, and then the negative 6 needs an x with it. Then I'm going to plug in 0 and negative 3. I plug in the 0 first, and if I want to, I can cancel the 4 and the 2 and get 2. So that's minus 2 times 0 squared, minus 6 times 0, minus, and then I plug in the negative 3. Negative 3 cubed over 3 minus 2 times negative 3 squared minus 6 times negative 3. And so the first part of this just ends up being 0 because it's 0 times everything. The second part is going to be potentially trickier. We're going to have to put this either in our calculator really carefully, or we may try to do it on our own, like with math, and whatever you want to do is fine, but either way you have to know how this mathematics all works. So if you're putting it in a calculator, you have to put it in exactly like what this says. Like the things that are important to realize is like this negative 3 needs to be in parentheses to the third power with a negative outside. The negatives don't just cancel each other out. In this case, if you did that, it would be fine because negative 3 cubed is a negative number, and then the negative in front makes it positive. But if it had been negative 3 to the fourth power, then that would not have been okay to cancel those negatives out. This negative 3 also needs to be in parentheses because it's being squared. The squared should be outside your parentheses. If you do this correctly, you should get the number 9 for this parentheses. And since there's a negative in front, that means that we have 0 minus 9, which is negative 9. So that's a lot of stuff there that can go wrong, that you have to be really careful to be able to actually see it through and get it all right. On 17, we add a power and divide, so this will be negative x to the 5th over 5 minus x to the 4th over 4 plus x cubed over 3. We're going to plug in 1 and negative 2. So when I plug in 1, when I plug in a positive number, the parentheses are not a big deal. Like I'm going to just like put this down here. When I plug in a 1, I do negative 1 to the 5th, and it doesn't matter if I put parentheses there or not. So for positive numbers, you can leave it off. The problem is with negative numbers. So that's my first part, is plugging in 1, and then I have to plug in negative 2. So this is where I need to put negative 2 in parentheses. And so depending on how much of this you want to work out by hand versus how much you want to put in the calculator, like make sure you know like negative 2 to the 5th power is a negative 32, and then the negative in front makes it a positive 32 over 5. But on this one, the negative 2 to the 4th makes it a positive, but it's negative in front, so that's negative. Like, you have to know these things and understand how order of operations work, unless you're just planning to put it in the calculator. If all you want to do is put it in the calculator, then you should be able to, then you just have to be careful to put it in right. So this first parentheses gives us negative 7 over 60, or obviously it might give you a decimal. Then you're subtracting, and the second one gives you negative 4 over 15. And so I would recommend you do one parentheses at a time if you're putting in the calculator, and then subtract them. And the answer to this as a fraction is 3 over 20, which is 0.15 as a decimal. Now, it doesn't really matter to me necessarily which one you put, because 3 over 20 and 0.15 are pretty similar answers as far as like how nice they are, but I would recommend that you either write this part in fractions or put a lot of decimal places and put the same decimal places for each. Like both of these, if you put it in the calculator, it's something like one of them gives you like 0.2666 repeating, and then the other one gives you like I don't know, something that subtracts and gives you 0.15, obviously. 0.1, I don't know. I don't know what it gives you, but like if you're not rounding carefully, you might not get 0.15, and that would be bad and sad, and you might get mad. So, 18. So on 18, this is x cubed on the bottom, which is like an x to the negative cubed on top. So that's my first change, and I'm not integrating yet because I haven't used any of my rules. So this is going to be x to the negative cubed. Then I'm going to use the power rule. So I add a power, get x to the negative 2, divide by a power, or that power, negative 2, and then I'm going to evaluate this from negative 1 to negative 3. If I want to, I can move the x to the negative 2 back down to the bottom. I can leave it on top. Like I could go ahead right now and just plug this in as like negative 1 to negative 2 over negative 2 minus negative 3 to negative 2 over negative 2. And as long as I type that in my calculator correctly, like I can get the answer just fine. The other way to do it is to move it down to the bottom and then plug in. And it's really up to you which way you would rather do it. It doesn't bother me either way. And so whichever way you do it, you should end up with negative 4/9, because this first part is negative 1/2, and the second part is 1 over 18 plus 1 over 18, because your negatives will cancel, and that gives us negative 4/9, which as a decimal is 0.4 repeating. This next one, you've been going along doing the power rule, and it's been fun, and so you even moved the last one up to the top. And so if you try that, if you move this up and make this x to negative 1, and then you try to use the power rule, you add 1 to your power, and you get x to the 0, which isn't so bad until then you realize you have to divide by that power, and dividing by 0 is a pretty big no-no. You're not really allowed to do that. And so if you get that far, that should be the point. If you haven't already realized that we need to look for a different way of doing this, like that should be where it happens. So this is going to be a natural log problem. Then the integral of 1 over x is natural log of x, so this is going to be negative 2 natural log absolute value x. I'm going to plug in negative 2 and negative 5. Now, those absolute value bars are pretty important. Whenever I plug in negative 2 and I plug in negative 5, those absolute value bars make the negatives go away. If I don't make them go away, I get an error on my calculator, and I don't know what to do to fix that. But if I'm like, oh yeah, absolute value bars, then this is really negative 2 natural log of 2 plus 2 natural log of 5. Now I want this as an answer because if I didn't have my calculator, that's as far as I could go. I also want you to put that in the calculator and tell me the decimal, which is 1.833. So this is 2 answers for this, one without calculator and one with. 20 is another natural log because it's just a positive, well, it's an x to the positive first power on bottom. That's how I know it's a natural log. The negative in front is going to make this be negative natural log of x from 2 to 1. And so this time the absolute value bars don't really matter because they're already positive. But what's important to know on this one is the natural log of 1 is something really cool. It's 0. And so that's 0, which means my answer to this without my calculator is just the natural log of 2. The natural log of 1 will always be 0. That is like one of those things that will never change. So this is negative 0.693 on my calculator. On 21 and then 22, whenever we get to the next slide, these are e to the x's. The integral of e to the x is e to the x, which is awesome. So we're going to evaluate it at 0 and negative 2. So 3e to the 0 minus 3e to the negative 2. E to the 0 is just 1, which means 3 times 1 is 3. I'm going to take the e to the negative 2 and move it down to the bottom so that it's a positive e squared. Now I'm going to get some common denominators here. So this has a 1 on bottom in the first fraction, so I need to times it by e squared to give it a common denominator. This is 3e squared minus 3 over e squared. That's my answer without my calculator. Then if I plug it into my calculator, I get 2.594. Same kind of thing on 22. The integral of e to the x is e to the x, so this will be negative e to the x, evaluated from negative 1 to 1. I want to plug those in. Negative e to the first minus negative e. That's not where I wanted that parentheses. To the negative first. And so negative e to the first is just negative e. This will be plus 1 over e. So I'm going to get common denominators of e. So this is negative e squared plus 1 over e, which as a decimal is negative 2.350. 23 through 25 are trig functions. So the first thing you have to do is figure out what trig function this should be. The integral of secant squared is tangent. So I'm going to put tangent x, and I want to evaluate that at pi over 6 and 0. So we're doing tangent of pi over 6 minus tangent of 0. To find these, I'm going to look at my unit circle. Tangent on the unit circle is y over x. So I go to pi over 6, and at pi over 6 is the point square root of 3 over 2, comma 1/2. So I'm going to put the y value, which is 1/2, over the x value, which is square root of 3 over 2, and simplify that. So that gives me the 2's canceling, and 1 over the square root of 3 is left. Then I'm going to do tangent of 0. So at 0 on our unit circle, the point is 1, 0. I put the y value over the x value. 0 over 1 is 0. So I do minus 0. I write my answer either as 1 over the square root of 3, or if I rationalize that for funsies, that's square root of 3 over 3. I don't want the decimals for this. If I wanted the decimals, you could have just plugged it into the calculator to begin with, but I don't want that. So 24. The integral of 2 cosine x is 2 sine x. And then we're going to plug in pi over 2 and negative 3 pi over 4. Now, what happens with the 2 in front is we're going to look at the unit circle and then times what we get by 2. So I'm going to look at pi over 2, sine is my y value, and I'm going to say, hey, that's 1. So sine of pi over 2 is 1, which makes this be 2 times 1. Looking at the unit circle gets rid of all of this, and we put what's there in its place. So I look at sine of negative 3 pi over 4. So negative 3 pi over 4 when you're looking at your unit circle. Positive 3 pi over 4 is up here, so negative 3 pi over 4 is below it, straight down. The y value there is negative square root of 2 over 2. So I'm going to do minus 2 times negative square root of 2 over 2. And I'm going to see what I can do to simplify that. 2 times 1 is 2. Negative 2 times negative square root of 2 over 2 makes a positive, and then these 2's actually would cancel because this is like 2 over 1. So that leaves me with square root of 2. On 25, the integral of sine x is negative cosine x. So I evaluate at pi and negative 3 pi over 4. And I'm going to plug in. So cosine of pi, cosine is our x value. Cosine of pi is over on the left side, so that's -1. So negative, -1. These two negatives can cancel and make a positive. Cosine of -3 pi over 4, we just looked at -3 pi over 4 on 24. The x value there is also negative square root of 2 over 2. So a negative 1 is a positive 1, minus square root of 2 over 2. If you want to, you can get a common denominator here and add these together and get 2 minus the square root of 2 over 2. Or if you left it as 1 minus square root of 2 over 2, that's cool too, because those are both fine answers.